to live interactive problem solving session for the course on traffic engineering. I am Seri Vinayagam, a PhD scholar in the civil engineering department at IIT Madras. So this is the week 7 of our sessions. And so let's start with an overview of what was taught in week 7 of this course. So this week was all about traffic control at intersections. Okay, so how do we analyze the traffic control that takes place at intersections? Okay, so in particular, we were looking at signalized intersections. So in the last week, so we looked at different levels of traffic control. Right, so we had level 1, which is a basic level of control. Then level 2, which is a semi-control, right, using stop signs, yield signs, or geometric features like roundabouts. And then we have the level 3, which is using signalized intersection, right? So when you have a high amount of traffic flow that you want to control, right? So and if there is a lot of conflicts that are present in that intersection, so then we go for a higher level of control, and so the signalized intersection comes under the level 3, right? And therefore it is also the more complex type of control to analyze with respect to the other controls that we have. So in the first lecture, so we looked at pre-timed signal design, right? So within the signalized control, so we have pre-timed and actuated controls, right? So in pre-timed, we have the signal cycle length. So every characteristic, right, that belongs to the control, like the cycle lengths, the phase sequences, right? So how the interval lengths. So all these will be fixed, right? So it doesn't vary from cycle to cycle. So that's what we have in the pre-timed signal, right? So fixed characteristic. It's compared to that. So we have actuated on the other hand. So actuated is basically demand responsive, right? So depending on the flow, right? So depending on the flow and also the type of flow that happens, right? So how much through movement comes, how much turning movement occurs. So depending on that, either the phase themselves might change, or the phase sequence can be changed, or even the cycle length, the green times, right, red times, all those can be adjusted so that we have a more effective signal control that's more optimal to what's the demand that we are witnessing in the field, right? So these are two broad categories. So within that, so we were looking at the pre-time analysis of these pre-time signals. So within that, so we first looked at the Webster's method. Okay, so what's Webster's method? So Webster's method helps us find the optimal cycle length. Okay, so the optimal cycle length CO is given by 1.5 L plus 5 divided by 1 minus sigma by A. Okay, so this is how we find the optimal signal cycle using the Webster's method, where L is here lost time, right? So again, as we saw from the previous week, so in every signal phase there will be startup loss and also a clearance loss time, right? So because vehicles will take some time, so the vehicles at the start of the cycle, so which are close to the stop line, so they will take some time to react when the signal turns green, right? So they will have a higher time headway, right, to cross the stop line. So we lose some time there. And similarly towards the end of the cycle, right? So when the vehicles where the yellow interval as well as the all red interval are available for the vehicles to cross, they may not fully utilize that, right? So they will decelerate and slow down, right? Because the signal the signal indication is going to change, right? So some portion of the total effective green that is available will be lost to startup and clearance first time. So the total sum total of that is what we have as L here, and YA is the is a ratio of the flow to the saturation flow rate, right? So this is your approach flow, right? So how much is coming in, right? So in the particular phase I, right? So this is taken as a summation over all the different phases that we have in the cycle, and SI is your saturation flow rate, right? So the ratio of these two is what this YI is, right? So we take it as sum over all the different phases, right? So again, within each phase, there could be you can have multiple approaches or multiple lane groups. So we have to take the maximum of all that, so which is what we call as the critical, this flow ratio, right? So that will give you the optimal cycle length. So this is called as the Webster's method. And then we also looked at two different concepts called critical lane and time budget, right? So as I was saying here, there could be multiple lane groups that can be present even within a single phase. So which and each of them can have different flow rates, right? So which of that we will consider in our analysis. So that's what this critical lane helps us decide. So critical lane is basically that lane group or the lane which will dominate, or which is the most critical one, right? So in terms of its in terms of having being susceptible to delay. So intuitively it will be the one with the highest flow, right? So but generally it's not, you have to consider the V by C, right? So with respect to capacity, right? So we have to see the approach flow rate, right? So whichever lane has the highest V by C ratio, so that is what is more critical, because as we know, when V by C is more than 1, we have oversaturated condition, which leads to delays that get carried over to multiple cycles, right? So therefore higher your V by C is, the more critical that particular lane is. And then the concept of time budget is basically how do you allocate the time that you have available. So if we take a 1 hour period, right? So and say a cycle length of 2 minutes, right? So you'll have 60 minutes, and each cycle is 2 minutes. So you'll have 30 cycles in 1 hour, right? So within each cycle, so you'll have multiple phases, right? So how do you allocate this 2 minute to the different phases, and how do you decide what is the proportion of the green time that should be allocated to these different phases, right? So that's that particular allocation that we make. So that's what we refer to as the time budget, right? So within that, so we looked at concepts like effective green. What is effective green? So it is your total cycle length minus your total loss time, right? So if you remove all the loss time, so whatever is remaining is there, for the vehicles to use to cross the intersection, right? So that will be a total effective green time, right? So this has to be proportionately allocated to the different phases, right? So based on again your V by C ratio, right? So the one that is more critical, or one that is having a higher demand with respect to its capacity, should get more time to clear to go past the intersection, right? So then we looked at planning level analysis, right? Again, so we in the last week, so we looked at three different types of analysis, right? So we got an introduction to it, so where we had planning analysis, design, and operational analysis, right? So the difference between them is in terms of the complexity of the analysis and also the data requirement, right? So the data requirement increases in this order, right? So planning is a very simplified form of analysis, right? So it is less complex, right? Also the complexity increases in this direction, right? And then we have the design analysis, and finally we have the operational analysis, which is the most detailed, complex analysis, right? So that is based on your actual field conditions, right? So we were concentrating on the planning analysis here, and we looked at the methodology of carrying out this planning analysis, right? So basically, the planning analysis tells you whether the solution that you are proposing is it sufficient, is it feasible, right? Or do you have to look into more or alternate solution, right? So that's what the objective here is. So what is the methodology that we will follow in the planning analysis? So basically, we first step is to determine the right turning, right? So whether we have to give a protected right turning or not, right? So how are we going to operate our the turning movements, right? So whether we give a protected right turn or we give a shared phase for the turning movements, right? So this is depending on the volume of the turning movement and the opposing movement, and also depending on the number of lanes that are available for the turning. So depending on that, so we have three different conditions which tell us whether we go for a protected phase or not for the turning operations. So that's the first step. So once we have decided that whether we, so that will tell us the phase plan, right? So then we have to convert all the volumes into through passenger car equivalents, right? So why? Because the turning movements have a different effect on the delay than the through vehicles, right? So basically, turning movement will take more amount of time compared to a through moving vehicle, right? So therefore, these are not equivalent. So when we say five vehicles, but if four of them are through vehicles and one is a turning movement, so that's different from another scenario where one is a through movement and four are turning movements, right? So there will be different time taken, even though there are five vehicles in both cases, right? So therefore, we have to consider or convert all these different movements into a single through passenger car equivalent movements, right? And also we have different kinds of vehicles, right? Like we have heavy vehicles, recreational vehicles. So we have to convert all of them into through passenger car equivalents for our analysis. So then what do we do? Then we have to decide about the lane groups, right? So we have to come up with the lane groups, right? So again, we looked at how do we determine the lane groups in the last week, right? So like exclusive, turning movements will be considered as their separate lane groups. Shared and through movements, they can be considered together, and through movements separately will form their own lane groups. So once we have the lane groups, we look at the flow rates for each of these different lane groups. So once we have the flow rates for each of them, so when there are multiple lane groups, we have to decide on the critical lane groups, right? So that's one of the things that we saw, right? So we have to determine the critical lane group for each phase, right? So and then once we have the critical volumes, then we go for the cycle length calculations, right? So we go for cycle length calculation, and once we have the cycle lengths, then the most part is done, right? So that's the basics. Then we look at the performance of this, right? So this is the solution for this intersection. This will be a phase plan, and this is the cycle length. So that gives you the solution. Then we have to analyze the solution, right? So we look at different performance measures, right? So we determine what is the delay, and then calculate the level of service for this particular solution. So that's the planning level analysis, and we looked at this methodology in detail in the second lecture. Then in the third lecture, we looked at the operational analysis, right? So operational analysis, as we saw, this is a more detailed one, right? So it's more complex, and difficult. Requires a lot of data, right? So you need more data, and so here we were three different lectures were provided to discussing the methodology for this operational level of analysis, right? So here we look at both movement groups as well as lane groups, right? So compared to lane groups, movement groups are simpler, classification of your different movements in the approach, right? So we consider both movement as well as the lane groups, and then flow rates for each of them, right? So the volume, right? So then we have to find the saturation flow rate, right? So then we have to calculate the capacity and also the volume to capacity ratio, right? So once you have volume and capacity obtained from your saturation flow rate, we can go for the V/C ratio, and using that V/C ratio, so we'll go for delay and LOS analysis, and also queue length analysis. Okay, so that's what we do, or the broad methodology that we follow in the operational analysis. And yeah, so finally, in the final lecture, we were looking at actually how do we analyze the queue length and the delay caused because of the initial queue that is present. And then finally, we also looked at pedestrian signals, right? So we also need to, remember that, the pedestrians will also be using the roads, right? So the intersections, will help them cross the intersections, right? So when there is no conflicting traffic moving on, right? For example, so when vehicle is moving in the north south direction, so pedestrians can also cross in the north south direction, right? So when there is no conflicting movement, right? So like that we can use the different phases where there is no conflict for pedestrian movements to allot time for pedestrians crossing the signal. So here the major considerations are, what is the time, that time taken, for reaction, right? So pedestrian, once the signal comes, the pedestrian will react to it, right? So it will take some time to perceive the the green that they get to cross, and then the time taken to actually cross, right? So this is for a single pedestrian, right? So and then we also look at the volume or the demand. What is the pedestrian demand for different directions of movement, and then the combined with this time, so that will give you how much time is required for clearing the pedestrian demand, right? So those are the two major criteria that will dictate what is the pedestrian signal requirement. Okay, so this is what was covered in week 7. Now let's look at some problems related to these. Okay, so the first question for week 7 is, which of the statements are correct with respect to Q at the end of analysis period, considering an initial Q, QB, and a V by C ratio at an approach of a signalized intersection? So options are, if QB is equal to 0 and B is greater than C, there will be no Q at the end of analysis period. Option B, if QB is equal to 0 and B greater than C, there will be Q at the end of analysis period. And C, if QB is greater than 0 and V is greater than C, the Q at the end of analysis period will be greater in size than the initial Q. And D, if QB is greater than 0 and V is less than C, the Q at the end of analysis period will be greater in size than the initial Q. Okay, so this is related to the the Q length analysis, right? So okay, let's look at how to what's the correct answer. So here we are looking at a multiple select question, right? So more than one of these options may be correct, right? So we are also looking for correct statements, right? So here two parameters are there. So one is the initial Q length, right? So which is denoted as QB, and then the volume to capacity ratio, right? So the volume to capacity ratio will tell us whether we have under saturation conditions or over saturation condition, right? So here if V is greater than C, we have over saturation, right? So V greater than C means it is over saturation condition, which will lead to buildup of tube, right? Because the capacity is not sufficient to clear all the volume that is approaching the signal, right? So therefore that is a bad thing. So if V is less than C, it is under saturation, right? So which means we have excess capacity than what is being used. Okay, so which is fine, which will not lead to excess delays. Okay, so we have to look at the combination of these two and then say what happens at the end of our analysis period, right? So whether there was an initial Q or not, right? So at the beginning of the analysis period, and then what happens during the analysis period is determined by your V by C ratio, right? So depending on these two, we have to say what is going to happen at the end of our analysis period, right, with respect to Q. Okay, so first is, if QB is 0 and V is greater than C, there will be no Q at the end of the analysis period. So this is incorrect, right? So initially there is no Q, that is fine. But what is happening during our analysis period? So our volume is more than capacity, right? So which means some q buildup will happen because this is oversaturated condition. So within our analysis period, whatever vehicles that came in to the intersection, so all of them will not be able to leave, right? So there will be some residual Q that will be left at the end of the analysis period. But here the option says there will be no Q, which is not correct. So option B says if QB is 0 and V is greater than C, there will be Q at the end of the analysis period. So this is correct. So right, that's what we saw just now. And C, if QB is greater than 0, which means initially there is some Q left, right? So before when we are starting our analysis itself, there is some Q there, that is QB, which is greater than 0. And during the period V is greater than C, the Q at the end of the analysis period will be greater in size than the initial Q, right? So this is also correct, right? So because there is some initial Q, and because V is greater than C, right, more vehicles are going to be delayed, right? So which means they are going to join the queue, right? Therefore, at the end of the analysis period, the queue length will be QB plus some delta, right? So this delta will be positive, right? Therefore, the finally the queue length will be larger than what it was there at the start of the analysis period. So C is also correct, and D is if QB is greater than 0 and V is less than C, the Q at the end of the analysis period will be greater in size than the initial Q. This is incorrect. Right? Why? Because so here we are looking at the opposite condition, right? So there was some Q present initially, but during the period we are analyzing, we had undersaturated condition, right? So we have some excess capacity, which means the vehicles that were initially there in the queue, so some of those can use this excess capacity or unused capacity to also cross, right? So therefore your queue will be smaller, right? So it can either be smaller, it can either completely dissipate depending on the condition, or there will be a queue that will be smaller than what it was there initially, but it won't be larger, right? So therefore D is incorrect. So the right options are options B and options B and C, right? So if you want to look at this graphically, so for all this queue length and delay analysis, it's usually easier to visualize using cumulative count curves, right? So the y-axis will give you the cumulative count of vehicles, right? And your x-axis will be representing time. Okay, so we have to draw the arrival curve and the departure curve. Okay, so we'll assume linear or constant rates through our analysis period, right? So analysis period starting at time 0, right? So we have two cases, right? So qb 0, qb greater than 0, right? Some positive value. Qb cannot be negative, right? Q length has to be 0 or positive. And we have v greater than c and v less than c, right? So let's look at 0 initial q, right? And v greater than c first. So if there is 0 initial q, so let's say this is our arrival curve. Okay, so slope represents the flow rate. Okay, so here arrival has a flow rate of v, and then we are looking at v greater than c, right? So which means the slope of the departure curve, so which will take place at a flow rate of c, right? And it will be, because v is greater than c, what we are seeing is constantly growing q length, right? So if our analysis period is 0 to t, right? So then this is our end of the analysis period. Okay, so the vertical difference between our arrival and departure curve represents the q length. Okay, so initially q length is 0 because these two curves are starting at 0, but because v is greater than c, over saturated condition, so the q keeps on growing, right? So at the end of the analysis period we have a larger q. So on the other hand, if we have something like this. So when your capacity is higher than your flow, so what happens? So even if there was an initial Q, so that will be clear. So with time you will have lower and lower Q length, or if there was no Q initially, so then there won't be any Q at all everywhere. So V is less than C. So both will be both the curves will be together. So if there was an initial Q, so how will it look like? So if there was an initial Q, so at time equal to 0, you have QB, okay, and then you will have flow happening, arrivals will be like this. And then if V is, less than C, so your departures, will catch up with your arrival at some time. Okay. So if your end of analysis period is somewhere here, you will have a smaller queue length than QB, right? So QB was here. Your queue length at time t will be smaller, and if your time was sufficiently larger, your queue length may be zero as well, right? So departure curve meets your arrival curve, and then they will go together after that. Okay. So that's the physically understand or visually looking at this different combinations of the Q length and VYC. Okay, so moving on to the second question. So the capacity of a lane group of a signalized intersection is 625 TPC per hour. So TPC is through passenger cars equivalents per hour. So already the conversion for the turning moments and the heavy vehicles have been taken into account and given in TPC. Okay, that is 625. The duration of each analysis period is taken as 15 minutes, and the demand flow rate for the lane group during each 15-minute interval is as given below. Okay, so we have the first 15-minute period, there is the demand of 645, and second 15 minute 637, third 15 minute 649, and in the fourth 15-minute period we have 657 through passenger cars per hour, right? So this is the flow rate. So the question is, estimate the length of the queue in TPC at the end of 60 minutes, assuming there is no initial queue at the beginning of the first 15-minute interval. Okay. Okay. So here, just like what we were explaining in the previous question, right? So what is here? So this is the capacity, right? C is 625. So this is constant, right? Your capacity is is not going to change with time, right? So this is constant, but your demand will change with time, right? So your V is constantly changing. But what we are seeing in each of this condition, each of this analysis period, your V is greater than C, right? So that will lead to some Q buildup, right? So there will be some Q. So we have to estimate what will be the length of the queue, not for each one, but we need we need it here, right? So at this time, after 1 hour, what is the total queue length? That's what we want to find. Okay, and given that initially there is no queue, right? So at the start 0, there was no queue, but during the analysis period, because V is greater than C, the queue is going to build up. So and after the 60-minute period, what is the queue length? Okay, that's the question. Okay, so how do we do this? Okay, so the answer is 22, but how do we get that? So the queue length at the end of the analysis period. So if we represent that using QE, so that is related to the queue at the beginning of the analysis period, QB, like this. So it will be QB plus T into V minus C. Okay, so here QE is Q at end of analysis period. Okay, QB is Q at beginning of analysis period. Okay, so T is duration of unmet demand, and your V is demand flow rate, and C is your capacity flow rate. Okay, so remember these are not the flows in the period, but the rate of flow. Okay, okay, and T is not your total analysis duration, but the duration where we have unmet demand. So what is unmet demand? So where V was greater than C, right? So when V is greater than C, that's when we have some demand which is not served, right? So on that unmet demand is this part. So this V minus C, so that is basically your unmet demand, right? So that is the excess demand, right? And for how long we had this V minus C, so that is what is represented by this T, right? So the product of these two will give you what is the unmet demand. So this unmet demand flow rate actually. So when you multiply it with the time for which that condition was existing, you'll get the unmet demand. So the unmet demand basically joins whatever Q was there at the beginning of the analysis period, right? So the sum of those two will give you the Q at the end of the analysis period. So we have to do this for each period separately and then sum them up. Okay. So we have the period. So we have four periods, right? So 0 to 15, then 15 to 30, 30 to 45, and then 45 to 60. Then we need to look at what is V, what is C. So what was the Q at the beginning, and then what is the Q at the end for each of these periods. Okay. So for the first period, what is the value of V? So 645, 637, 649, and 657. 645, 637, 649, and 657. Okay, so this is our volume demand flow rates. Capacity, it is constant, right? So 625. And we know that at the beginning of the analysis period, so which is the time 0, for the first period, QB is 0, right? So there was no Q to start with. Okay. So now basically for each of these periods, we have to calculate QE. Okay. So for the first period, what QE will be? So QE will be 0 plus. So what is T? T is basically 1/4 of an hour, right? So 0.25, right? So it is 1/4 of an hour because our analysis or the flow rates are given in terms of TPC per hour. So we have to take T also in hours. Okay. So multiplied by V minus C. So V is 645, C is 625. Okay. So this is 20 into 0.25. So 0 plus 0.25 into 20. So which is 5. Okay, so that is your Q at the end of the first analysis period. Okay, so now what happens? So whatever Q was there at the end of the first analysis period becomes the Q at the beginning of the second analysis period, right? So because these are continuous time periods. Okay, so whatever is the end will become the beginning of the next period, right? So whatever QE we have here, so that becomes the QE for the next period. Okay, then we have to repeat it. So for the second period, QE will be 5 plus. So the duration where V is greater than C, it is for the whole duration, right? So for this whole 15-minute duration, our V is higher than C, so that's why we are taking the whole of our analysis period as the T. So multiplied by again 637 minus 625. This will be 5 plus this will be 3. Therefore, the Q at the end of the second analysis period is 8. Okay, again this will become your Q at the beginning of the third period. So again, so what it will be for the third period, 8 plus 0.25 into 649 minus 625 is 8 plus 0.25 into 24. So 614, right? So that is for the third period. And for the final fourth analysis period, so same thing. So QE is this time 14 plus 0.25 times 657 minus 625. Okay, so that will be again 14 plus 8, that will be 22. Right, so finally at the end of the analysis period, which is at 60 minutes, so what we have is 22 vehicles. Okay, so that's how we find out what is the Q at the end of our analysis period. Okay, so here because we had constantly the volume was greater than capacity. It's a for like suppose if it was if it was something else, right? So if it was only for the 10 minutes in our first 15-minute period where we had 6:45, and then for the last 15 minutes, if we had something like 6:20, so in that case, we cannot do it like this, right? So we have to split it up, right? So our T will be 10 into then 6:45 minus 6:25 will be only for that 10 minutes instead of the whole 15 minutes, right? So that's what we need to be careful about. But in this problem, for the whole period, our V was greater than C. So our analysis period, so which we will usually represent it using T, was equal to the period of our unmet demand. Okay, so that's why it was 0.25. So moving on to question number 3. Here we are looking at signal timing design using Webster's method. Okay, so the given intersection has two-phase signal system and the equivalent hourly volumes in vehicles per hour for all the approaches are shown in figure. So here is the figure. All red time per phase AR is 1 second and loss time per phase is 4 seconds. Okay, so we have four approaches. Okay, the eastbound approach has 340 vehicles per hour, westbound 420, southbound 450, and northbound 550. Okay, and here we have a two-phase signal design. Okay, phase A is for the east-west movement. Okay, so eastbound and westbound, so they have a saturation flow rates of 1200 and 1300 vehicles per hour per lane. And the second phase, phase B, is for the north-south movement. Okay, so there are no turning movements here. So the northbound and southbound have 1400 vehicles per hour per lane as the saturation flow rate. Okay, so the question is, so there are three parts. So the first part is to find out this summation YA for the different phases. Again, what is YA? So YA is your the critical flow ratio, right? So the approach flow to your saturation flow rate, right? So that you have to take for the critical lane group and then sum it up for the different phases. So that value we have to find out. Second, we have to find what is the optimal cycle length, right? So because we are using Webster's method gives us the optimal cycle length. And third is find the total effective green time, right? So once we have the cycle length, so we have to estimate what is the effective green time in that cycle. Okay. So here are the answers for the parts, right? So sigma YA is 0.716, optimal cycle length is 70.4, and the effective green time for the total cycle is 60.4 seconds, right? So, okay, how do we get this? So the first part, I think it is simpler. Okay, so here let's write the given data first. So we have the phases. Yes, we have phase A and phase B. Okay, so in each phase, what are the different lane groups that we have? So for phase A, it's basically the eastbound and the westbound movements, right? So those two will be the two different lane groups. And for phase B, we have the northbound and the southbound movement, right? So those are the two phases, two lane groups, right? So each phase has two lane groups. And for each lane group, so what do we have? We have QI. So QI is your, through equivalent, lane volumes for per lane, right? So again, we have no turning moments here. So already we have the equivalent, lane volume. So for the eastbound movement, it was 340. For the westbound movement, it was 420. And then we have for the northbound, it was 550. And for southbound, it is 450. Okay, so this is your, flow, volume, incoming volume. And then you have to have the saturation flows. So what is your saturation flow? So again, that is given data. So for the eastbound, it is 1200. Westbound, it is 1300. For the north and south, it is same 1400. Okay. So once you have this, you can easily calculate what is YA. Right. So YA. So first you have to before YA, let's calculate the ratio QI by SA. Right. So this is for each lane group. So for the first one, it is what? 340 by 1200. So that comes out as 0.283. For westbound, it is 420 by 1300. So that is 0.323, right? So this is for phase A. Next for phase B, right? So this is for eastbound, this was for westbound. For northbound, we have 550 by 1400, so that is 0.393, and finally we have southbound, so that is 450 by 1400, so that is 0.321. Okay, so we cannot ya is not sum of all these four values, right? So ya is the sum of these flow ratios for the critical lanes. Okay, so here, so critical lanes has to be calculated for each phase separately, right? So for phase A, right, so we have two flow ratios. So one is for the eastbound, another is for the westbound, right? So two lane groups. Out of these two, only one of them will be critical, right? So which is basically the maximum of these two, right? So the critical flow ratio, that is what ya is for each phase. So that will be what? So maximum of these two, that is 0.323. That is for phase A. And then for phase B, maximum of 0.393 and 0.321. So that is 0.393. Okay. So for two phases, we have two critical flow ratios. Okay, and finally, the question was to find the summation of this YIs 1 to 2 or A to B. Okay, so that will be YA plus YB, so 0.323 plus 0.393, so that is 0.716. Okay, so that is option for the first part A. So the second part was to find use the uh, Webster's method to find out the optimal signal length. Okay, so Webster's method, so how do we use it? So Webster's method, the optimal cycle length is 1.5 L plus 5 divided by 1 minus sigma yi, right? So here we calculated this denominator sigma yi in the previous part, right? So all we need to know is the L is the total loss time. Okay, so this we have to take for the whole cycle, right? Not just for each phase. And what is given to us is the loss time per phase is 4 seconds. Okay, so and then we have an all-red time that is equal to I think 1 second. Okay, so we have 1 second of all red and then 4 seconds of total loss time per phase, right? So both of this is per phase, but L is for the whole cycle. So L will be 4 plus 4 plus 1 plus 1, right? So this is loss time. This is your all red time, right? And this is for both phases, phase A, phase B. Similarly, here also you have phase A and phase B. Okay, so basically 2 times of 4 plus 1. So in total, 10 seconds is lost, for the whole cycle. Okay, so that is your capital L. So it will be 1.5 into 10 plus 5 whole divided by 1 minus. So sigma yi is 0.716 from the previous part. So 15 plus 5, 20. 1 minus 0.716, so that is 70.4 seconds. Okay, so this is your optimal signal cycle as per the Webster's method. Okay, so that is second part. Third part was to find the total effective green time for the whole cycle. That is easy. So total effective green time is nothing but your cycle length minus your total loss time per cycle. Okay, cycle length we calculated as 70.4 and loss time is 10 seconds. So this is 60.4 seconds. That is your total effective green time in the whole cycle. Okay, so that's how we calculate the effective green times and use the Webster method for cycle length. Okay. Next, moving on to question number 4 is match the information given in column X with its corresponding effect on the base saturation flow rate. So column X, we have three effects. So one is the lane width is equal to 4 meters. Second, area type is CBD, and third is lane width is 3 to 3.9 meters. Okay, and the effects given in column Y, one A is increases, B is remains constant, and C is decreases. So these are with respect to the base saturation flow rate. Okay, so here are the different matchings that are given. Okay, so we have to say what is the effect of these different changes on the base saturation flow rate. Okay, so what is the base saturation flow rate? So as we have looked at in earlier weeks, so the base condition will tell you is for an idealized condition, right? So for certain set of values, for different factors, you have a particular value for that parameter, right? Here we are talking about saturation flow, right? And for any deviation from this base condition, right, so in the field condition is what the actual conditions are. So if there is any difference in the field condition from the conditions that were used in the base calculation, so we have to adjust the base value to according to the field conditions, right? So that's what we will be doing here. So what is the base saturation flow rate? So it is usually taken as 1900 vehicles per hour per lane, right? So when you have higher population areas, right? So for lower population areas, so this I think it is 1725, right? So these are the base conditions per hour per lane. Right, so this is given for certain conditions of lane width and a particular area that we are looking at. So first is so the thing is the base condition considers lane width of 3 to 3.9 meters, right? So which means this is the option 3. This is same as the condition in the base case, right? So which means that there is no change that we have to make if this is the case, right? So the lane width is 3 to 3.9, then we need not adjust the lane width. So therefore this will remain constant, right? So because it is equal to the base condition, so 3 should be matched with B. So which means that so any deviation from that, so here we have a lane width of 4, it should affect your uh, you know um, saturation flow rate, right? So which means it's going to either increase or decrease. It's not going to remain constant. But which is it? Because so the saturation flow rate is 3 to 3.9, but the lane width now we are looking at is higher than what we have in the base conditions, right? So which means you have wider lanes. So wider lanes means there is going to be more capacity, right? So therefore your saturation flow rate will be higher, right? So therefore it should increase. So one should be matched with A. And finally, we are looking at area type of CBD, right? So again, for CBD areas, so that's not what we usually assume in our base saturation flow rate. And again, in the city centers or the central business districts, so we'll generally have a lower saturation flow rate, right? So therefore, it should be decreased from whatever is the base saturation flow rate, right? So therefore, this is the right matching. So 1 is matched with A, 2 with C, and 3 with B. So that is given in option B, right? So B is the right answer. So B is the right answer. Okay, so moving on to question number 5. Which of the following statements are incorrect with respect to analysis of incremental delay in operational analysis of signalized intersection? So option A is that incremental delay factor K accounts for the effect of controller type 1 delay. Option B is the upstream metering adjustment factor is 1 for all coordinated intersections. C, the variance in number of arrivals per cycle decreases with increasing V by C ratio. And D is the value of K is 0.5 for actuated controllers. Okay, so here this is coming from the operation analysis, right? So far we are looking at the planning analysis. So here we are looking at operation analysis, and within that the delay analysis, right? So again within delay, right, so we call this as control delay because we are analyzing delay due to a traffic control system. So that will have 3 parts, so D1, D2, and D3. So D1 is your uniform delay. D2 is the incremental delay, right? And D3 is delay that is caused because of initial queue that may be present. Okay. So now we are looking at the second term, which is the incremental delay. So the incremental delay has two adjustment factors as given here. One is the incremental delay factor, another is the upstream metering adjustment factor. Okay. So the formula for that is the D2. Let's D2 is 900 into T. T is your analysis period taken in hours into x minus 1. X is here v by c ratio plus square root of 1 minus x or x minus 1 the whole square, because we are squaring it, doesn't matter, plus 8 ai x divided by ct. Okay. So here are the two those two factors, k and I, right? So k is here incremental delay factor, I is here upstream filtering factor. Okay, so why do we have it? So the incremental delay factor, it is there for to account for the different controllers that we have, right? So as we looked at earlier, so there are pre-time controllers and actuated controllers, right? So in pre-time we have fixed settings, whereas in actuated, the cycle characteristics will be changed according to the demand and the type of flow that is happening. Okay, so but delay is not different, right, for these two controllers. So this k factor is what adjusts for the effect of these different controller types. So A is correct, right? So, but the question is to identify the incorrect ones. But A is a correct option. B is upstream metering adjustment factor is 1 for all coordinated intersections. So the upstream metering factor is the I factor, right? So it is basically, so it captures the effect of the signals that are that are present upstream to the signal that we are analyzing, right? So depending on how the signal upstream operates, the queue might be affected in the downstream signal that we are analyzing, right? So this will take into account of that. And if the signal that we are analyzing is an isolated signal, right? So without an influence of any upstream signals, so in that case, this I will just be 1, right? So, but in the controlled intersections or coordinated intersections, so this will be different. Okay, so B is incorrect, right? So because it says 1, the value is 1 for coordinated intersection, but it is 1, which means there is no change. That is true only for the isolated cases, right? So not for coordinated intersections. And C, the variance in the number of arrivals per cycle decreases with increasing V by C ratio. So this is true, right? So this is again with respect to the previous, the upstream signal, right? So if it has a high V by C ratio, which means that you have close to capacity conditions or oversaturated conditions in the upstream signal. So the flow that will be coming out of your the upstream signal, right? So which is your arrivals for the signal that we are looking at. So it won't be varying too much from cycle to cycle because you have excess vehicles, right? So you'll have flow that is more or less equal to the saturation flow rate, right? And the saturation flow rate is a constant, right? It's not going to change for that intersection, and you will have flows that are very close to your saturation flows, right? So therefore the variance in the number of arrivals will be lower when you have higher V by C ratios, right? So that is also true. And finally, the value of k is 0.5 for actuated controllers. So this is incorrect. It's a value of k is 0.5 for pre-time signals. Okay, and for actuated signals, depending on the controller, you will have different values of k. Right. So therefore, the incorrect options are options B and option B and option D. Right? So therefore, that is the right answer for this question. Okay, question number 6. So here we are looking at the planning level analysis as per HCM 2016. So there is this figure shown here. shows the ring diagram for a planned three-phase signalized intersection. All the equivalent hourly volumes given in the figure are in vehicles per hour. The target V by C ratio is 0.92. The loss time per phase is 3 seconds. The sigma yi is 0.752, and the base saturation flow rate can be taken as 1900 passenger cars per hour per lane for all the approaches. So we have to find the total critical lane volume, the estimated cycle length for the given target V by C ratio, the effective green time for phase B, and then assuming that phase B has only one lane, what is the capacity of that lane for phase B? And finally, the incremental delay that is associated with this lane group, which is actually a single lane for phase B. Okay. So here we'll be following the methodology that we looked at for planning level analysis. Okay, so we have three phases, phase A, phase B, and phase C, right? So each phase there are two rings in the controller, R1 and R2, controlling different movements. Okay, so first what we have to do is find the total critical lane volume, right? So how do we do that? So the critical lane volume, so here are the answers. So it is the answer is 1428. How do we get it? So for phase A, so in ring 1 and ring 2, right? So according to the figure, so we have 258 as the flow and then 232 as the flow, for for the movement controlled by ring 2, right? So critical, right? The critical lane group will be the one with higher V by C, because we take we can assume the capacity is constant, so V by C will be higher for the one with higher V. Okay, so here the maximum of these two is 258. Then for phase B, again we have two lane groups. So the first lane group has 556 and the second lane group has 720. So here 720 is the maximum. And then for phase C, we have two lane groups in ring 1 itself, 450 and 90, right? So if you look at the figure again, so we have the through movement and the shared left turn, that is one lane group, and then the right turn is a separate lane group, right? So it is not with the through movement. So therefore we have two different lane groups in ring 1, and then similarly in ring 2 also we have two different lane groups with 78 and 420. So here, how do we find it? Here we have to take the maximum of all these four. Okay. So maximum of 450, 78, 90, and 420. So that is 450. Okay. So this is the max, right? Volume. So this is equal to critical volume. Okay. So then this is for each phases individually. Now the question was, what is it for the whole cycle? So basically we have to sum it up for each phase. So that will give us the value for the whole cycle. So 258 plus 720 plus 450. So that is 1428 vehicles per hour. Okay, so that is the solution for part A. So part B, the question was to find the estimated cycle length for a given V by C ratio. Okay, so here we have to find a desired cycle length for a for a given target VBC, right? So here we are not looking at the Webster's method that gives you the optimal cycle length. So optimal cycle length means it is the cycle length which produces the least delay, right? So but here our objective is different. Our objective is to attain a given V by C ratio, right? So it is not to get the least delay. So we cannot use the Webster's method for that. So here to get the desired cycle length, right? So the formula is L into x divided by x minus sigma y. Okay. So here, so the x is here, or we can call it as xt. So xt is your target V by C ratio. Okay. So xt is equal to target V by C ratio. So L is your total loss time, and IA is your critical flow rate, flow ratio. Okay. So what is your total loss time? So total loss time is, so for each phase we have a loss time of 3 seconds, right? So and we have three phases. Okay, so L is three phases. And this is the number of phases into 3 seconds. This is loss time per phase. So this is in total 9 seconds. Okay, so xt is given as 0.92. Okay, so xt, yeah, xt is your target V by C ratio, so that is 0.92. Okay, and then sigma yi is 0.752. Okay, so we have everything that we need. So the desired cycle time would be 9 into 0.92 by 0.92 minus 0.752. So solve it, you will get it as 49.3 seconds. Okay, so that is your desired cycle length, for a target V by C ratio of 0.92. So the third part was to find the effective green time, not for the whole cycle, but only for the phase B. Okay, so how do we do that? So to do that, we have to first start with finding the total effective green time for the cycle, right? So that is C cycle length minus the total loss time. Okay, so cycle length is 49.3 seconds. And the last time was 9 seconds. So we have 40.3 seconds of effective green time. Okay, this is for the whole cycle. Right, so here this is where we, the time budget concept comes in, right? So we have 40.3 seconds available with us in each cycle. So we have to allocate this 40.3 seconds of green time to the three phases that we have, A, B, and C. Okay, so how do we do that? So we do that proportionately based on the the V by C, or the V by S ratio, right? So whichever lane has the highest critical volume, so that lane group will get higher green time. Okay, so because it has a higher demand to be served. So for phase B, the effective green that will be allotted is the total green. So this some portion, some proportion of this total green. So that will be whatever is the critical volume for lane B divided by the critical total critical volume for the whole intersection. Okay, or for the whole cycle. So that is 40.3 multiplied with what is it for lane B, it was sorry, phase B, it is 720, right? So 720 is the critical volume going through phase B, and in total we had 1428 for the whole cycle, right? So in that proportion, so we will allocate the 40.3 seconds, right? So that will be coming out as 20.3 seconds. Okay, so that is the effective green time for phase B. Then the next question was to find out what is the capacity of the lane loop in lane 2, right? So how do we do that? So capacity is related to, I'm using small c, right? So capacity for that particular phase, so it will be equal to the saturation flow rate into here effective green ratio. Okay, so GB by, so SB to GB by cycle length. So C is here. Okay, but when you are using lane groups, so there can be more than one lane, right? So this saturation flow rate will be for per lane, so we have to multiply this by the number of lanes that are there in that particular lane group. Okay, and what is the saturation flow rate? So the base saturation flow rate is 1900 passenger cars per hour per lane. This is true for all approaches. Okay, so 1900, because this is per lane, right? So we have to multiply it by NB, and NB is 1. So that is given the question, right? So we were asked to assume that there is only one lane that is corresponding to the lane group for phase B, right? So therefore it is 1, so equal to the base flow. So into the effective green ratio, so effective green for phase B, we just calculated 20.3. And what is the cycle length? Cycle length is 49.3, right? So we used here 49.3. So this will give you what is the capacity for the lane group corresponding to phase B. So this is 782 vehicles per hour. Okay, so that is the capacity. Okay, and then the final question was to find out the incremental delay that is associated with the lane group corresponding to phase B. Okay, so in planning level, so the formula differs for the so earlier we saw one formula but with K and I, right, for incremental delay. So that is from the operation analysis, right? So for the planning analysis, it is slightly different. So in the incremental delay component D2, the formula for that is 225 times. Okay, so x is again the b by c ratio, so plus root over x minus 1 the whole square plus 16 times x divided by c for that phase. Okay, so I'll put I. So I represents the phase that we are analyzing. Okay, so Ci is the capacity. So which here we are looking at for phase B, right? So which means this I will be corresponding to phase B. Okay, all these values that we will be substituting will be corresponding to phase B. Okay, so what is XB? So CB we know. What is XB? So XB is nothing but the V by C ratio, right? So but again, so the V whatever we have been given, so that is all per lane, right? So we have to multiply this by the number of lanes as well, but because the number of lanes in lane group is 1 for phase B, so it is 1 into volume was 720, right? So divided by what is the capacity? Capacity we just estimated as 782, right? So here, so xb is equal to 0.921 for phase B. So the incremental delay component is 225 times 0.921 minus 1 plus square root of 0.921 minus 1 the whole square plus 16 times 0.921 divided by 782. Okay, so that is the capacity for lane group B. So you simplify that, you will get it as 17.86 seconds, right? So this is the incremental delay component, right? So this is so we had the uniform delay, so this is the incremental delay. So that is 17. Okay, so we have found out all these different components coming from the planning level, right? So here all we needed was the different phases, right? So we can assume different things, right? So because this is a planning level analysis, we can assume certain things, like for example we assume the base saturation flow rate, the number of lanes. It's all this we can do at a higher level. Whatever data is available we can use that, whatever is not available we can go for assumptions using the base conditions. Okay, question number 7 is which of the following statement is correct with respect to back of Q? So the options are: third term of the back of Q size Q3 accounts for Q caused by sustained oversaturation during the analysis period. The second term of back of Q size Q2 accounts for Q caused by initial Q during the analysis period. And option C is Q size includes both partially as well as fully stopped vehicles. And D is the first term of the back of Q size Q1 accounts for Q caused by signal cycling through its phase sequence. Okay, so again this is from the queuing, the analysis of Q links in the signal intersection. So again, so for the Q size, so we have the three components Q1, Q2, and Q3. Okay, so these three Qs, Q links are because of different causes, right? So we count for these different causes. Okay, the question is talking about which term corresponds to which cause. Okay, so here he says the third term is to account for the Q sustained over caused by sustained oversaturation during the analysis period, right? So again, this is due to the V by C ratio being greater than 1, right? So this is what caused sustained oversaturation, right? So because when V is greater than C, so you will have Q that will be carried over to the future cycles. Okay, so that is what we are looking at, but that is not taken into account by the Q3 term, right? So that is actually the second term, right? Q2 is what accounts for the sustained oversaturation. Okay, therefore A is incorrect. So B is second term, that is Q2 accounts for Q caused by initial Q during the analysis period. So again, we already saw in A that Q2 is for sustained oversaturation Q. Actually, this is what is Q3. Okay, so these are saying interchanged things, right? So Q2 is sustained oversaturation, Q3 is because of whatever was there initially. And C says Q size includes both partially as well as fully stocked vehicles. So again, incorrect because only this part, fully stocked vehicles, is correct. Okay, partially stocked vehicles is not correct. Okay, so only vehicles that are fully stocked are considered to be part of your queue. Okay, so vehicles that are partially stocked, which are slowing down, so they have not, joined. They are not considered to have joined the queue. Okay, so once they are fully stocked, then only we consider them in the queue. Okay, so therefore C is also incorrect. So finally, we have first term Q1, which accounts for the Q caused by the signal cycling through its phase sequences. So this is correct. Okay. So because of the change in the the signal indications, right, so on the different phases, so we will have some queues that are forming, right? So if all the vehicles were not able to cross through, right, in that particular phase, so we will have some queues that are forming, right? So even when v is less than C, right, so not always if your signal settings are such that all vehicles that came in could not go through, right? So still you will have some queues formed. So Q1 is for that signal operations, which naturally leads to some queues being formed. Right? So D is the only correct statement out of all these four. So the right answer is option D. Okay, then moving on to question number 8 is which of the following statements are correct with respect to interpretation of the results obtained from the operational analysis of signalized intersection? The options are if xc, which is the v by c ratio for the whole intersection, that is less than 1, but for some lane group xi is greater than 1, then there are no capacity deficiencies for any lane groups. Option B is if xc is less than 1, but some lane group has xi greater than 1, then reallocation of the cycle time can be considered. C is if xc is greater than 1 and some lane group also has xi greater than 1, change in the intersection geometry may be suggested as one of the improvement strategy. And option D is if the intersection V by C is less than 1 and for all the lane groups X is also less than 1, then it represents that the cycle time is generally not appropriately allocated among the phases. Okay, so here we are, so here we have done all our analysis. We got the critical V by C, okay, for each phases, right? And then we took the critical value for each phase and then obtained the critical V by C ratio for the whole intersection, right? So it will be some value, right? So less than 1, equal to 1, or greater than 1, right? So how do we interpret this? So that's what we looked at in the lecture. So here we are answering question related to it. So first one is the condition where the intersection is having less than 1 or equal to 1 V by C ratio, but some lane group, right? So that is having xi greater than 1. Okay. So in this case, it says that there are no capacity deficiencies for any lane group, right? So that is obviously incorrect, right? Because so capacity deficiency means your capacity is less than your capacity is less than your volume, right? So this is the capacity deficiency. So this implies here V by C is greater than 1, right? So V is greater than C. Okay, So that we, because we have some lane group where xi is greater than 1, for that lane group, here v is greater than c, which means there is a capacity deficiency for that lane group, right? So, but the statement says it is not present for any lane group. So therefore, the first option is incorrect. So second option is the intersection is undersaturated, but some lane group, is oversaturated, and reallocation of the cycle time can be considered, right? So this is true, right? So this is one of the strategies. So because some lane group has capacity deficiency, so we can try to allocate more cycle time or more green time for that lane group which is having xi value of greater than 1. Okay, so therefore it, because it has a more volume, so you can give more time for it. So that can be one of the strategies to alleviate this capacity deficiency. So B is correct option. And C says if xc is greater than 1 and some lane group also has xi greater than 1, change in intersection geometry may be suggested as one of the improvement strategy. Okay, so this is also correct. So here the lane group is also having capacity deficiency, and the intersection as a whole is also having some capacity deficiency. So here, so because we are not having adequate capacity for the intersection as a whole, so maybe we have to look into intersection, changing the intersection geometry, like providing more lanes, right? So for those critical approaches, right? So that is also one of the strategies that we can consider when the intersection as a whole is having a lesser capacity, right? So therefore C is also correct interpretation. And D, if xc is less than 1 for all lane groups, xi is also less than 1, then it represents that cycle time is generally not appropriately allocated among the phases. This is incorrect because the intersection is also fine, right? So every lane group is also fine, right? So which means our solution, the cycle time is fine, right? So it's not causing any excess delays. Therefore we cannot say that it is not appropriately allocated, right? So because the cycle time is appropriate for all the phases, we have the critical v by c is less than 1. So therefore there is no issue with our cycle time, right? So no actual issues with our cycle time allocation. So but this says that it is other way, right? So therefore D is also incorrect. So the only correct statements are B and C. And so B and C is the right answer. Okay, question number 9 is for the given intersection is shown on this figure. So the eastbound movement has two lanes. Okay, so here we have eastbound. So this is our eastbound. This is here northbound. Okay, there are only two movements. The eastbound movement has two lanes. The northbound movement has only one lane. Assume that all volumes shown have been converted to the compatible through passenger car equivalent, right? So the TPC values, and the signal at the given intersection has two phases with the following characteristics. Lost time is 3 seconds per phase, saturation at V is 2.5 seconds per vehicle. And so what we have to calculate is the absolute minimum cycle length that can be used, and then the desirable cycle length for a target V by C ratio of 0.9 during the worst 15 minutes of the hour if the PHF is 0.95. And C is consider an additional lane added to the eastbound direction, right? So which is the third lane, and then the volume per lane drops down to 400 vehicles per hour per lane. So then in that case, what is the desirable cycle length for that situation with the V by C target V by C ratio being 0.9 and the PHF being 0.95. Okay. So again, this is the planning level analysis that we are going to do. So first is the absolute minimum cycle length, right? So we have, if that's what we want, like, so what is the absolute minimum, like? We can't go less than this. Okay, so that is our absolute minimum. So the answers are here. So let's see for the first one, how do we get the absolute minimum cycle length? So that is given by NTL divided by 1 minus the critical divided by the saturation flow rate. Okay, so here so TL is your lost time, total lost time, which is 3 seconds per phase. Okay, and N is your number of phases. So number of phases is 2. Okay, so this is here N, right? So TL is this. So this is saturation headway is small s, sorry, small h. Okay. So we have N, we have TL, and we have H. So we need VC. So what is VC? VC is your critical, flow. So here we have only two lane groups, right? So one is in the eastbound direction, another is in the northbound direction, and so we have to sum it up for both of these phases. So first phase it is 600. This is for the eastbound, and for the northbound it is 650. So 1250. Again, this is TPC per hour. Okay, so because it's already converted, right? So 1250 is your critical volume, critical flow. So N is 2, TL is 3 seconds. 1 minus 1250 by 3600 by H is, I think, 2.5. Yeah, H is 2.5. So this denominator here is your saturation flow rate, right? So 3600 by H will give you the saturation flow rate. So this is 45.5 seconds. Okay, so that is for the first part, the absolute minimum cycle length. Okay, the second part was to find the desired cycle length for a target V by C ratio of 0.9, right? So here our objective is to achieve the target V by C ratio of 0.9, right? So we have to adjust the cycle length some way so that the V by C ratio will be 0.9. Okay, considering that during the peak hour we have 95% of the whole hourly traffic. Okay, PHF is not 0.9. So in that case, how do we do it? So the C desired is given by, so the numerator is the same. It is the total loss time for the whole cycle divided by 1 minus, so VC by, so this part is also the same. We consider the VC as well as the saturation flow rate, but we also take into account the PHF and also the target V by C ratio, right? So I'm calling it as XT, like in the previous questions that we have done. Okay, so again we have everything that we need, right? So we have N, two phases, 3 seconds lost per phase by 1 minus VC is 1250 as we had calculated, divided by 3600 by 2.5 is the saturation flow rate, into PHF is given as 0.95 and target V by C ratio is 0.9. Okay, so if you calculate this, the desired cycle length will be minus 392.9 seconds. Okay, so here, so obviously this is not right. Why? Because the cycle length is coming out to be negative, right? So which is not possible, right? So we cannot have a negative cycle length, right? So it has to be a positive quantity, but it is coming out to be negative. So what does that mean? How do we interpret this? The interpretation is, we cannot achieve this target V by C ratio of zero point 0.9 under the given configuration, right? So what is that? So the given configuration is for this, demand, right? For this demand and this saturation flow rate and loss time that we have in this two-phase configuration, no cycle length can give you a target V by C ratio of 0.9, right? That's what this negative cycle length is implying, right? So we cannot set any cycle length and get this 0.9 as our V by C ratio. So that is simply not possible. That's what it means. Then the third part is we have to do the same thing, but now with for a different condition where we have an additional lane, which means we have, instead of two lanes that was there initially, we are going to have three lanes. Because we have more lanes, the demand, the flow rate per lane is going to reduce, right? So from 600 it now becomes 400. So now can we have some cycle length which will give target V by C ratio of 0.9? That's the question. So we have to just repeat this analysis for this new condition where we have three lanes. Okay, so the number of phases and the total and the loss time per phase, that's not going to change, by 1 minus VC will change. VC again will not change because you have just so the V has not changed, right? So only sorry sorry, the VC will change. Yeah. So earlier we had, so this part for the northbound movement there won't be any change, right? So it is 650. The number of lanes has remained constant, but now for the eastbound movement there is a change, right? So therefore VC should change. So VC earlier it was 600 plus 650, but now it is 400 plus 650, which is 1050. Okay, so because we have an additional lane, so the critical lane volume for the eastbound movement has reduced. Okay, so this part has changed. So therefore VC has changed. So 1 minus VC. So rest of the things are the same. So 3600 by H 2.5. PHF doesn't change. And the target PVC ratio is also not changing. So in this case, we solve it. So we get C desired as 40.8 seconds. Right? So here this is a positive value, so this is possible, right? So if you give a 40.8 seconds as the cycle length, right? So 41 seconds, so we can achieve a target VBC ratio of 0.9 if the eastbound movement has 3 lanes, right? Instead of 2 lanes, there's 3 lanes with 400 vehicles per hour in each lane. So in that case, 41 seconds will give you a target VBC ratio of 0.9, right? So therefore, for part C, the answer is 40.8. Okay, question number 10, the final one for this week. So you have to accept or reject the given statement. So the statement is, as per the planning level analysis for an intersection, the absence of a protected phase for right turning vehicles is justified if there is more than one right turn lane on the approach. Okay, so we have to either accept or reject it. So the answer is we reject this statement. So why? So again, in the planning analysis, the first step itself is this, right? So we have to decide whether we are going to have a protected phase for the turning moment or not, right? So we have three conditions in the analysis that tell us whether the protected right turn is justified or not, right? So the first condition is if you have, I think, the turning moment volume is more than, I think, 240 vehicles per hour, then you must have a protected phase for that. Or if your turning moment volume into the product of the turning moment volume and the opposing moment volume, I think if it is more than 50,000, when there is one lane in the opposite direction, and similarly there are other values when you have 2 lanes and 3 lanes. I think for 3 lanes it is 110,000, right? So 3 or more, right? So 3 plus lanes, right? So if this condition is satisfied, then also you have to provide uh, you know a protected phase for the right turn, right? Why are we doing this? Because there is a huge volume, so there can be more conflicts, right? So the gap that is available for these vehicles to go through, if we have not provided a protected phase, will not be sufficient, right? So that will hinder these turning moments, right? That's why we have these conditions, right? So you have one, when you have turning movement itself is too large, so we provide we have to provide them. Second is the combination of turning movement and opposing movement, right? So where is the conflict happening for the turning movement? It is with the opposing movement, right? So suppose we have like a southbound movement like this, and then we have a turning movement, right? So from towards north and then turning right. So we have a conflict with this oncoming traffic, right? So when the oncoming traffic is large, then this conflicts will be higher, right? So for the turning movements, right? So that's why the second condition is there. The third condition is what this question is about, right? So where we have the number of right turn lanes, right? So when you have more than one right turn lane, so then also you have to provide a protected phase for the right turning. Okay? So why we rejected the statement? Because it says that the absence of a protected phase is justified if more than one right turn lane is there in the approach, right? So this is opposite, right? The presence is what is justified. The conditions given here tell us when it is necessary to give the protected phase, right? So which means that if these condition, any of these conditions is satisfied, then we must provide a protected phase, right? So but this statement says the opposite. It says the absence of it, or we should not provide a protected phase if there is more than one right term length. So that is incorrect. Therefore, we are rejecting this statement. Okay, so with that, we are coming to the end of week 7. Okay, so if you have any questions or clarifications that you need, you can make use of the Q&A forum that is available on the SWAYAM portal. Okay, so with that, we'll close the session for this week and we can meet again, next week, Saturday. Okay, thank you. See you next week.